Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syamer. I am from BMFR and my group member is Muhammad Haziq and Muhammad Afuan. For this video, I will show how fluid mechanic work, and this is the mini experiment example to show how fluid mechanic work. First, the thing you need is the cardboard, a cup, and fill the cup with the water. So, for the experiment, you need to put the cardboard on the cup lid and then turn the cup upside down. After that, you can see the cardboard is not falling down. How this happen? So, for the next video, I will explain how this happen.
Now let me explain to you why the water does not spill out from the glass. The reason of why the experiment works is because of air pressure. Air pressure is the weight of a column of air pushing down on an area. An object in air is subject to pressure from air molecule colliding with it. At sea level, the mean air pressure is 1 atmosphere or 1 atm, that's equal to 101 Pascal. This air pressure is pushing up the cup from below while the water is pushing down on the cup from above. In this experiment, the air pushing out from underneath the paper is strong enough to overcome the weight of the water that pushing down on the paper. Because of air pressure is pushing up on the cup will stay on the glass and the water will not spill out. It's more easily to understand the whole experiment by looking at the force of the water rather than on the card. The card transfers the force from the air pressure upward to the water. So, there is a pressure of almost 1 atmosphere pushing up on the water from below. Of course, there is also a pressure from the air inside the glass pushing down on water from above. The air inside the glass was originally at 1 atmosphere of pressure when you put the cup over it. But when you invert the cup and remove your hand, the water moves downward a very slight amount, thereby increasing the volume a lot to the air. As the air expands to fill this increased volume, several things happen at once. The air molecules spread out so that fewer of them hit the edges of the volume each second, and they slow down so that they don't collide with the container quite as forcefully. As a result, the air pressure goes down a tiny bit according to Boyle's law. Now, the pressure inside the glass pushing down is not as great as the outside pressure pushing up, and this pressure difference is enough to counteract the gravitational force pulling down on the water. Once the cup sets enough so that these three forces balance, everything will stay put. For a typical size of glass about half full of air and air volume increase of less than 1% generates a big enough pressure difference to support the weight of the water.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq Hilmi, number metric B0520100035. Now I want to explain by using calculation for the experiment. Okay, firstly, you must draw the glass and the cup. This is before. This is a cardboard and this is a little space of air. This is 0.5% air gap. After the glass is upside down, this is 1% air gap. After that, we must show the experiment by using free body diagram. We assume that 200 milliliter water in glass. We have 1.0% air gap, and we have two force. This is force inside and force outside. After that, we got the volume of water is 200 ml. We convert the 200 ml to 200 times 10 power of negative 6 meter cube. After that, we got the formula P1 times V1 equal to P2 times V2. That's after that, we calculate the pressure and volume at before. Firstly, the pressure in pressure 1 is 1 atm. The atmospheric pressure is 101,325 Pascal. After that, the volume is 0.5% times 200 times 10 power of negative 6 meter cube. After that, we got the 1 times 10 power of negative 6 meter cube. After that, we calculate the velocity, the volume after the upside down V2, 1% times 200 times 10 power of negative 6 meter cube. We got the 2 times 10 power of negative 6 meter cube. After that, after we got the P1, V1 and V2, we calculate the pressure 2. The pressure 2, we got the P1 times V1 over V2. After that, after we calculate, we got the 50,665 Pascal. After that, we calculate the force inside. Force inside equal to pH plus P2 times area. pH is hydrostatic pressure, P2 is 50,663 Pascal. How do we calculate the hydrostatic pressure? Hydrostatic pressure is pH equal to rho GH. 1000 is rho is as a density times 9.81 as a gravitational times 0.15. 0.15 is a height of the cup. After that, we got the hydrostatic pressure is 1471.5 Pascal. After that, we calculate the area of the cup. Area of the cup is area equal to pi r squared. R is 0.075. After that, we got the area is 70.9715 times 10 power of negative 3 meter square. After we got the area hydrostatic pressure, we will calculate the force inside. Force inside, we got 921.2927 Newton. After that, we calculate the force in outside. Force outside equal to atmospheric pressure times area. Atmospheric pressure is 101,325 times the area. We got from this calculation. We use same area because this is a same cup. After that, we got 1790.5647 Newton. After that, finally, we got the force outside is greater than force inside. Force outside is 1790.5647 Newton is greater than 921.2927 Newton. After that, we will conclude the experiment. The force in outside is greater than force inside. That's why upside down will happen. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. For the video, we will discuss about a real life example of a product or process of fluid mechanics. The product that we choose for the video is barometer. What is barometer? Barometer is a scientific instrument used to measure atmospheric pressure, also called barometric pressure. The atmosphere is the layer of air wrapped around the Earth. That air has a weight and press against everything it touches as gravity pulls it to Earth. Barometer measure this pressure. One of the example barometer is mercury barometer. The mercury barometer is the oldest type of barometer invented by Italian physicist Evangelista Torricelli in 1643. Torricelli conducted his first barometric experiment using a tube of water. Water is relatively light in weight, so a very tall tube with a large amount of water had to be used in order to compensate for the heavy weight of atmospheric pressure. We start with a long narrow tube filled with a liquid of specific weight, gamma, and a shallow pan that contain the same liquid. Both containers are open to the atmosphere. Then, the long narrow tube is inverted and placed into the shallow pan. This process must be done carefully so that no air enters the tube. Even though no air enters the tube, some of the liquid will flow out of the tube into the pan, creating an elevated space at the top of the tube. Liquid molecule will evaporate into this space and eventually an equilibrium will be established between the rate of evaporation and the rate molecule return to the liquid bulk. The pressure caused by the evaporated molecule at equilibrium is the vapor pressure PV. The head of the liquid column H is dependent upon the liquid column weight. The air pressure force pushing downward on the exposed liquid in the pan, and the vapor pressure force pushing downward on the top of the liquid column. Okay, next. We now can apply Newton's second law in the vertical direction for just the liquid column. The sum of the forces acting on the column is equal to the column mass times its acceleration. Since the column is at a rest, its acceleration is 0. Next, we identify the forces acting on the column in the free body diagram. The column weight act at the center of mass and point downward. The vapor pressure act at the top of the column and push downward with a force equal to PV times the column cross-sectional area. Since the liquid column is not moving, there also must be a pressure force acting at the bottom of the column. Recall that the pressure does not change as you move horizontally through the static fluid. Let's label a couple points of the barometer. Since point A is at same elevation as point B in a continuous fluid, the pressure at point A must be same as pressure at point B. So the pressure force acting on the bottom of the liquid column is the atmospheric pressure times the column cross-sectional area. Then Newton's second law become the atmospheric pressure PA times A minus the vapor pressure PV times A minus the weight. The weight is equal to the mass of the column times the gravitational acceleration G. Mass is equal to the liquid density times the volume of the column, and the volume of the column is equal to the column height times the column cross-sectional area. Notice that we have combined density and gravitational acceleration into specific weight gamma. Plugging in the expression for weight into Newton's second law and eliminating A to the liquid specific weight times the column head plus the vapor pressure of the liquid. So we can determine the atmospheric pressure by simply measure the head of the liquid column and looking up the specific weight and vapor pressure of the liquid, both of which are usually very easy to do. For the next slide, historically, a common liquid used in a barometer was mercury. Here, abbreviated by its chemical symbol Hg. Mercury was used because its specific weight is relatively high, approximately 13.6 times greater than the specific weight of water at room temperature. Looking at the barometric pressure equation for a given atmospheric pressure PA, if the specific weight increase, the column head decrease. In other words, using a liquid with a high specific weight, such as a mercury, mean you could use a barometer with a shorter column length. For example, under typical atmospheric condition, a mercury barometer would have a column head of approximately 3/4 of a meter, while a water barometer would have a column head of over 10 meters. So it is much more practical to use barometer that has mercury instead of barometer that has water. Mercury has an additional property that makes it a good choice for use in a barometer. For typically atmospheric condition, the vapor pressure for mercury is many order of magnitude smaller than atmospheric pressure, so we can say PV from the equation, and are left with the atmospheric pressure being approximately equal to the specific weight of the liquid times the column head. Common unit of barometric pressure are mm, also called a torr or inches mercury. At 15 degrees Celsius and 1 atmosphere of pressure, the column head of a mercury barometer would be 760 mm or 29.92 inches.